Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This is the fifth one in the series on elastic strings and springs, and we're using vectors. In this particular one we're going to look at the use of vectors to calculate work done. Now, so far, for a constant force, we've used the relationship that work done is the force times the distance moved in the direction of the force. It's essentially a one-dimensional setup, is that. Now, if we have the force oblique to the line of displacement, it becomes more complicated. So there's a diagram showing the displacement of distance d along that dotted line. That's going to be undertaken by that point of application of the force F. So the question is, what's the work done? Well, in this case, if the force F doesn't act parallel to the direction of motion, we resolve the force to find a component in that direction, and then the expression becomes that component, F cos theta, times the displacement. Now that you'll recognise if you write it in the form Fd cos theta is essentially the scalar product of the vector F, and now that replace d by a vector d, which is the displacement vector. So we're talking about a situation where the work done is F cos theta times d, where the F cos theta is seen as the component of F in the direction of the displacement, but we can think of it also as Fd cos theta, which constitutes the scalar product of F and d, with a dot used for that form of product, and where the d has been converted into a displacement d. So the notation we're going to use is to say that we can express it in vector form. If F is the force and x is the displacement, then it will be F dot x. Remember that if you're using handwriting, that should be written as F underlined dot x. In a screen display such as this, heavy type is used for vectors to make it more convenient, but in handwriting you must underline the vectors. Right, notation for vectors, that's just what we've been talking about. Let's look a bit more closely. You've got the alternatives 3, 2 or 3i plus 2j. Now printed books tend to use 3i plus 2j because the publishers want to save money, and 3i plus 2j results in a more compact form. But for precisely that reason it's more difficult to understand. So always make a rule, work in columns. And that's what I'm going to do here. So if I see 3i plus 2j, I automatically re-see it, if you like, or revision it as a column 3, 2. Well, let's take a particular application of what we've been saying. A particle moves forwards on a straight line and it's acted upon by a force. And that force in a column will be 70, 30. Find the work done as the displacement is 2i minus j. Well, it will just be the scalar product of 70, 30. The scalar product is indicated always by a dot, 2 minus 1. Remember from pure maths that can be expressed in terms of the products of the corresponding components, and you add the sums to get the products together. So we get 70 times 2 plus 30 times minus 1, which gives us 140 minus 30. So that gives us our answer of 110, and expressed in context that will be 110 joules. So there's a tidier version of the calculations, and there's the sentence to give the answer in context. Well, let's look at something slightly more complicated. Here we've got again a force 70i plus 30j, which I automatically see as 70, 30 in a column, and the work done is required where the displacement is given in more complicated terms. It's 2.6 meters and its direction is that 512 vector. So let's draw a picture. There's a representation of the vector 512. It's along the hypotenuse of that triangle 512, and the Pythagoras calculation tells us that the length of 512 is 13. So we can't simply take 70, 30 dot 512, because if we do, we'll have gone too far. We need to take the fraction 2.6 divided by 13, that's how much of 512 that we want to get the right length of displacement. So that's worked out then in the usual way. We can see that 2.6 over 13 is 0.2, so it's 0.2 times, and then you'll have 70 times 5 plus 30 times 12, which is a bit of arithmetic to work out, not terribly complicated, and so we can see that finished there. The bracket shows the products of the corresponding components to get the scalar product, and then we multiply by 0.2. So the answer finally is 142 joules. There it is in context. Well, that brings us to the end of this particular video. The next one is on work done by a variable force.